So for our last talk, I'd like to introduce Dimitri Feys from Missouri Science and Technology, and he's going to talk about slump and pumping, and also another provocative title. So with that, Dimitri.
All right, well, thank you, Shiho. Glad to see you all over here, celebrating the anniversary of the slump cone, and with Pete's presentation, 100 different ways of using a slump cone on site potentially as well. So first thing I want to do is acknowledge my two co-authors over here, Geert de Schutter and Victor Meschering, two Europeans that have been actually heavily involved in a little review project we had a couple of years ago on pumpability. So slump has been used to predict pumping pressure. I will say to people, I see the average gray hair scale in the room is not too bad. But for those that are really on the gray spectrum of things, then you probably remember a whole bunch of graphs like, hey, slump is the measure to predict pumping pressure. And I'll show the graph in a minute, right? The question is that true? So here we go. So the first thing I'll do is actually show those historical old graphs and what's going on. And then we'll see if we need to debunk the theory that slump actually works, yes or no. We'll see what's going on. So what you get over here is a graph to predict pumping pressure. It's an old one, right? And you need to make 3/4 of a circle to actually get things done, right? So let's, all right, hey, I got a little arrow over here. That's gonna work. All right, so you start with your flow rate. And this is European units. You get the thing in American units in the next slide. Where is it? All right, so you start with flow rates, then you got your pipeline diameter, you look for the crossover, then you go down when you got your crossover, and then you look at the proportional length because there's some correction factors for curves and for bends and reducers and so on. And then you cross over again, and then you have a qualification. Here it's the German version. You get the spread, which is a flow table test, which may not be related fully to yield stress and so on. But in the end, you come to predicted pressure, and then you can select your pump. That's how it works, right? And you have an older version, but that's ACI 304 from 1998. Similar concept, but instead of having a spread right here, it says it's a slump. And at that point, we still had low slump concrete. But, you know, what's playing the role? So we got the flow rates, we got the diameter, we got the pipeline or the equivalent length of the pipeline, and then we have a workability characteristic coming into play. And what you get is pressure and potentially your desired pump or your desired power of the pump you need. So let's extrapolate. If I believe that graph, the higher the slump, the lower the pressure. Right? Because the slope is getting lower and lower, so if you intersect, we're getting to the lower pressures you're getting there. So I put two purely hypothetical, these are no funded anywhere, just two hypothetical lines in here. What happens if I had an 8-inch concrete slump? Or what if I get SEC? That's what's supposed to happen according to these graphs if I'm able to extrapolate that's the condition, right? So it should be really easy to pump self-consolidating concrete according to that theory, right? Question, is it? And I've dug up some old graphs from when I was still doing my PhD. This is just a pressure loss flow rate relationship for a conventional vibrated concrete with a slump of 8 inches and a really decent self-consolidating concrete with a slump of 30 inches. Now it's European style self-consolidating, and let's not discuss that the red curve is actually curving, but you need more pressure to pump SEC. Oh, what? That doesn't make sense, not according to what we just saw. So something's going on. Something's not right. And Pete, thank you very much for the rheology reminder. I really don't need to introduce too much, but at a given time, you get two factors that play a role. It's yield stress. The stress needs to start or stop the flow, and then the viscosity is the stress to increase the flow rate or to accelerate the concrete. Now, what's really happening inside those pipes? Right? So let's fix our pressure. Let's fix our pressure loss. Once we get that, and I'll take that giant arrow back out. If we fix our pressure loss, and there's a fundamental law that states, it's the equilibrium of forces, says that your shear stress distribution in your pipes will look like this red line over here. Independent, whatever I put in there, it doesn't matter. Whether I put oil, ketchup, wine, whatever, it doesn't matter. It's going to be a linear relationship, right? And then what we need to look at is, let's focus on the SEC first. I have a low yield stress, right? So I have a high slump. It's shown that there's a there's a really decent correlation between yield stress and slump. So what I'm going to do is actually find a location in that pipeline where the shear stress does not exceed the yield stress. And if I got this, and my graph is a little off, But what I have is a straight section over here, but I have no velocity gradient. I have a constant velocity moving through. Now, outside of this zone, I get shearing. Outside of this zone, we're dominated by viscosity, because the viscosity will determine how much that shear rate or how much that velocity gradient will be. Now let's move to conventional vibrated concrete, and we get two case scenarios. It could be still within that shear stress zone, or it could be outside of the shear stress zone, which means theoretically there's no flow. This is happening, my yield stress is higher than any of the shear stress I apply, nothing happens. Now wait, you get flow. It has been shown you get flow. That's what again Pete alluded to, that is you have that lubrication layer being formed. It's the concrete's nature saying, hey, I find a way to flow a little easier than just shearing the entire thing by ourselves, right? So that happens, and for SEC it happens as well. You get those lubrication layers, right? So what determines that velocity profile? So for a flowable concrete, is the yield stress will determine how much of that center zone is being sheared and how much is not, but the viscosity will determine the shear rate gradient in the concrete that's being sheared and also inside that lubrication layer. For conventional vibrated concrete, and let's not have a strict distinction that there's no shearing in conventional vibrated concrete. It can happen, small pipes, high pressures, you'll get there, right? Well, let's assume that this is the condition it happens, is the yield stress will determine whether that bulk concrete is being sheared yes or no, and again, it's not a simple answer, whether it's straight yes or straight no, right? And then the viscosity of the lubrication layer is what will dictate flow rate. The yield stress of the lubrication layer does not really matter too much, right? So, other thing is that the viscosity of the lubrication layer is related, it's not a perfect one-to-one, but it is related to the viscosity of the concrete. So yield stress is just determining the thickness of that zone, and that's about it. So, science. If I pump oil doesn't have a yield stress, right? And if I change the viscosity of the oil, I'm going to change the pressure I need to flow at a certain flow rate, right? So if you look back into anything fluid mechanics, is the yield stress is your, not because the viscosity is your primary factor that is affecting, especially in laminar flow, of any material in a pipe. So for concrete, you get that lubrication layer is being formed, it facilitates flow, pressures go down by about a factor 5 to a factor 10 compared to not having a lubrication layer, and even if it goes completely friction, then totally different story. But the viscosity of the lubrication layer will determine what's happening. So I don't really have yield stress coming into play, but it has an influence. It's not zero, right? So again, it determines how much of that concrete is being sheared. So how much of the concrete is seeing shear rate. That's what it does, but the effect is inferior to viscosity. Now let me show you. Dug up some more results from the past. This is an instrumental pumping circuit that we used in Canada about 10 years ago. So we got a little pump over here. Now we got a decent pump over here. 4-inch pipeline over here, 2 pressure sensors, so we get pressure loss, and then the 5 inches on the way back. But we'll focus on the 4 inches to move forward. And let me show you what the effect of specific mix design factors is on pumping pressure. And the first one I go through is water to cement ratio. And yes, we went extreme, right? 0.22 is not really a fun concrete to work with. But let me say it this way, they are self-consolidating or close to self-consolidating. So by adjusting that water reducer content, we keep yield stress and the slump or slump flow approximately, or not 100% successful, but approximately constant. We get about a factor 15 difference between the 0.34 and the 0.22. It's a huge difference in pressure. And actually, from a mix design perspective, once we get to that type of concrete, there's nothing else that has that much of an effect on pumping pressure. So if you ever need to pump a 0.25 water cement ratio concrete, ask yourself the question, do I really need 0.25? Can I go to 0.27? It's really going to help you. There's nothing else that can help you as much. Now let's do the same thing. Let's do the effect of slump flow. Right? We put them all down here. Right? And again, we keep the water cement ratio constant. The only thing I need to point out, I had a slight change in paste volume between the top 3 curves and the bottom 5. So that may play a role as well. Yes, so there is an effect of yield stress. Right? There's something there. Well, let's combine things together. Let's do this. So I got pressure loss as a function of flow, or slump flow. Slump or slump flow. I like, wow, this is a great graph. I love it. right? Look at that correlation coefficient, 0.88. If dealing with concrete science, concrete rheology, and so on, you get 0.88. It's like, hooray! It's fantastic. It looks good. If you keep all the other parameters constant, because there's a big white spot in my graph. Because if I start changing the other things up, the speeds graph show, slump versus viscosity. I got pressure versus slump over here. At constant flow rate, constant pipe diameter, it's a cloud. Yes, I got that series of black points, but we didn't change anything else. It's just, the slump of the concrete. Yeah, it works. But everything else is way much more spread over the graph, right? So is that really so important, right? So it's not looking so good anymore, right? If you change the other parameters, it really doesn't work. And I want to show you a similar graph, which is pressure loss versus viscosity. And I didn't want to put an empirical test in there. I just put the viscosity values in there. And that works. It works really well, to be honest, right? R squared of 0.91, like hooray, 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 right? So really looking good. And there's one point that deviates. This one over here. And that's the only concrete we had with 2-inch slump at that point. Right? So yes, yield stress will matter and will cause some deviation from the graph, but that one big point over there is the one because the yield stress is really high in that case. So it deviates due to slump. Right? So the measurements we did with all these different mix designs and so on confirm that we have a much larger influence of viscosity on pumping compared to the yield stress. So there is an effect, but the effect is minor compared to all the other changes we've introduced into the concrete mix design. So, can we predict pressure with means of slump? Is this scientific fact? No. Is it historical coincidence? I would say yes. Right? Because, go back 50 years and, those ladies, the few there were, and the gentlemen that developed those graphs, I'm not saying they developed total nonsense. No, they actually went through a bunch of results, put their experience together, and came up with the graphs, and it made sense at that point. So why did it make sense? Why do those really old graphs at that time, why did they work? And again, with the average grayscale we have, let's go back 50 years. I know for some of us, including myself, I wouldn't be here. All right, but let's try to go back 50 years. And how did we influence workability 50 years ago? Water? Paste. Right? So let's look at the consequences. But conceptually, it comes down to the same thing, yes. Fully agree. So what's the effect of an increase in water on the rheology? Well, yield stress is going to go down, or viscosity is going to go down. What's the effect of increasing paste on the rheology? Well, yield stress is going to go down, or viscosity is going to go down. So what happened, right? So with the techniques we had in the 70s and the 80s to increase workability, yield stress and viscosity were influenced in the same way. That's why it worked. Right? That's why it worked, because it's dominated by viscosity scientifically, but it's a correlation with yield stress, just because at that point it worked. Right? So with the invention of and the implementation of our third generation plasticizers, starting in the 90s approximately, now we really have the capacity to influence those rheological parameters individually. The 0.2 water cement ratio with a 25-inch slump flow was not really possible in the 70s. Right now we can. Huge viscosity, very low yield stress, it is possible. So as such, the use of slump to predict pumping pressure is a historical coincidence, as slump, yield stress, and viscosity were influenced by the mix design factors in the same way, right? It no longer is. So that's the new one. And again, that's a graph coming from my colleague in Dresden, in Germany. Very similar thing. I'll get my big arrow back up. So very similar graph, it just slightly changes a couple of things, right? So we still got the flow rate to start. We've still got our pipeline diameter. Now these things have been flipped, right? So we still have the length in here. We still got pressure, but we have a different parameter that comes into play here as a concrete characteristic. And the way they looked at it is this little equipment over here has been developed, what's much and then commercialized and so on, is a sliding pipe diameter. And it actually measures pumpability, what they can, and the graph here is just a certain set of raw data that we get from that little device. So we make a flow at different speeds by adding different weights actually on here. If flows down, you just drop it down, and it flows at different speeds. And there's a pressure sensor actually sitting right here in the middle, and that measures the pressure you have. And what they can do is calculate or relate the pressure to the flow rate. And they define two parameters. Right? Based on that graph, you get an intercept A, which in this case is negative, so you still on graph, but you get the slope B. And the slope is the indication of the viscosity, and that's the one they actually put in that new nomogram, which seemed according to them to work. So, with this, that's the end of my presentation. Let me just amend my title a little bit. Using Slump to predict pumping pressure, it is a historical coincidence. Thank you very much.